Hi students, this is Miss Galton. I'm sitting here at my dining room table with my children. This is
Aya.
And this is
Leo. Hello.
And I'm here to review the logistic growth model with you. And Leo and Isla are going to do their own thing and try to be quiet so that I can make a video. All right. So you are responsible as calculus students for understanding the logistic growth model. Because, again, this test is open notes, you're not responsible for memorizing anything. And even in a normal year, I've never seen the College Board ask you to go from the differential equation to the function itself. They just ask you some questions to make sure you understand the logistic growth model. So I'm going to review a couple of things about the logistic growth model. First of all, it turns out that dy dt it approaches horizontal in two different places. So horizontal would mean that, the logistic growth model approaches horizontal. The derivative approaches zero in two different ways. So one way would be, because this is in factored form, so we have 0 equals ky times m minus y. One way is if k times y equals 0, and k is a constant and k is not 0, so that would happen if y is equal to 0, if we have no population. If we have no population to grow, then that would just be a horizontal line. It wouldn't be much of a logistic growth situation because you have no population. But as you can see, as our y-coordinate gets close to 0, our slope also gets close to 0. The other way that we can have a 0 derivative is if m minus y is equal to 0, or if y is equal to m. M is the carrying capacity for our population, and y actually can't exactly hit m. Y can only get close to m. So we have a horizontal asymptote at m, at y equals m, but we don't really actually hit that point. So the idea that you need to know about the logistic growth is that dy dt is always increasing. It's always positive. As you can see, we've got this uphill
In our backyard.
on the graph. Our graph is an uphill graph. I said it's always increasing, but I meant it's always positive. And the y has two horizontal tangents. Horizontal asymptotes. One of them is at y equals 0, and the other one is at y equals m, the carrying capacity for this population. Okay. The other kind of question that you get asked about logistic growth is you sometimes get asked, when is the growth rate the fastest, or what is the population at the inflection point? So inflection point is where the second derivative changes sign. Growing the fastest means that we're looking for a max or a min on the growth rate, so we would need to take a derivative of the growth rate. So we're going to take a second derivative, and we're going to do that implicitly. But before we do, it's actually easier to take the second derivative if we distribute here. So if we have k times m times y minus k times y squared. Now when we take the derivative here, k and m are constants, so that derivative is k m times dy dt minus k is a constant, so 2k times y to the 1 power times dy dt. And then we look for like terms, and it looks like if we wanted to factor this second derivative, we could take a dy dt out, because both terms have a dy dt. And we could also factor out a k, because both terms have a k. So I'm going to go ahead and do that. So we have k times dy dt times m minus 2y. We've already talked about how k is a constant, it's positive. dy dt is never exactly 0. We just have places where it approaches 0. So the only way for the second derivative to equal 0 is if m minus 2y is equal to 0. So the way for the second derivative to be 0 would be if 2y is equal to m, or if y is the carrying capacity divided by 2. So the y coordinate of the inflection point is m over 2. And that's also where the growth rate is the fastest there. I pointed out that this is another way of writing the logistic growth equation. All of the math that we've done so far still works with that equation as well. I want to point out that these are different k's. They've expressed their growth constant differently in these two equations. So it looks like the same k, but they're different constants. It's a little bit like c when we have a plus c. I would have the logistic growth equation solved for y in my notes since this is an open notes test, but I find it unlikely that they would ask you about that. They are much more likely to ask you about the logistic growth differential equation than the equation itself. All right, that's a quick summary of things you should know about logistic growth. Oh, I said one more thing. In the logistic growth equation, the y equals equation, the one thing that doesn't come straight from the differential equation, so you can't fill it in exactly, is this capital A. That's a constant that will change depending on your initial population. So in order to find that capital A, you'd have to plug in your initial population. But you can go straight from the differential equation to this. You can replace this m with the carrying capacity, and you can replace this k with the k and this m with the carrying capacity. But in order to solve for A, you need an initial condition. Okay. That's everything about logistic growth.
Bye.
Bye. Leo wants to say bye.
Bye.
Isla, do you want to say bye?
Bye.
All right. See you later.